When you silenced your phone's alarm with a single tap this morning, you may not have realized you touched a device bearing the mark of one of the planet's most complex machines, ASML. In recent years, this company has become so critical that it can even ignite geopolitical tensions between countries. From Apple's iPhone to NVIDIA's AI chips to Tesla's autonomous driving, ASML's technology works behind the scenes of everything we rely on. I'm Halil Ibrahim. Today we'll look at an extraordinary story that begins in a quiet Dutch town and stretches to the center of global technological rivalry. This isn't just a company story, it's the story of the invisible skeleton of the modern world. From the high-NA revolution born of 20 years of persistent effort to geopolitical restrictions, clogged supply chains, and the technology of 2030. And together we'll ask, can a single company truly change the rhythm of the world? Grab your tea or coffee, get comfortable, and let's begin. It all started in 1984 in a small wood-roofed shack in Veldhoven, in the south of the Netherlands, its roof leaking. From the outside, it looked ordinary. Inside, a team that didn't believe in the word impossible was at work. Their goal was simple yet ambitious enough to change the game, writing with light at smaller and smaller scales. At the time, giants like Nikon and Canon ruled the industry. The rules seemed already written, but this team had the engineering intuition and stubborn patience to rewrite them. The company was born as a joint venture between Philips and a small Dutch equipment maker, ASM International. On paper, it had great potential. In practice, it was Philips offloading risk in a technology it no longer saw as highly profitable. Budgets were tight, resources limited, but the vision was sharp and clear. In the dominant stepper machines of the era, the wafer table stayed fixed while the lens moved to write pattern. ASML's engineers did the opposite. They kept the lens still and moved the Wafer-Stage with astonishing precision and speed. That concept later evolved into the TWINSCAN architecture, a two-stage choreography. This choice became the first revolutionary step that delivered both speed and alignment accuracy over rivals. A third evolution introduced the dual-stage approach, exposure and alignment proceeding simultaneously, which sent operational throughput soaring. The early years were anything but easy. Prototypes were tested again and again. Many failed. But one day, the critical bolt clicked into place. Mechatronics solutions for ultra-precise stage motion took root. Meanwhile, the foundation of the ASML-ZEISS partnership was laid. The company embarked on a journey that demanded the world's flattest, smoothest multilayer mirror surfaces in optics. Over the years, this supplier link turned into a strategic advantage. Why is a chip's fate tied to vibrations at the nanometer scale? Think of the slight breeze that hits your face the moment the metro doors open. A tiny air movement in a huge structure affects you instantly. Lithography is similar, except we're trying to etch a city map onto a grain of rice with light. At such scales, the tiniest jolt can shift a street onto the sidewalk and an intersection into an alley. That's why ASML's machine moves the wafer, the silicon disc, as if it were gliding on glass. A massive granite block absorbs vibration. Smart isolators dampen shocks. Laser sensors measure position at every moment. While the stage is dynamically controlled in 6 degrees of freedom, interferometry and image-based measurements validated roughly 20,000 times per second. Thermal stability is maintained at the millikelvin level. This integrated discipline makes sub-nanometer alignment accuracy possible. Inside the machine, 2 stages work at once. One precisely aligns the next exposure while the other prints the pattern. Then they switch roles. This choreography raises both speed and accuracy at the same time. It was ASML's first standout dance on stage. Technical brilliance alone wasn't enough to unseat the industry's giants. The company needed to make money, and for a long time, it didn't. In the early 1990s, founding partner Philips began to reduce its risk. As Philips pulled back, ASML found itself on the edge of a cliff. Just then, a new name rose from another corner of the map, TSMC. Not yet a legend at the time, this Asian foundry believed in ASML's machines and reached out a helping hand. The partnership changed the trajectory of both companies. In 2000, during TSMC's Hsinchu fire crisis, ASML's high-throughput line stepped in like a critical backup lane, further strengthening the trust between them. Even so, the most pivotal move of the story had yet to appear on stage. The big bet that would make ASML unrivaled years later was still waiting to be placed. For years, 193 nanometer DUV light carried the show. At one point, Immersion, like filling a magnifying glass with water, helped us get closer. But as features shrank further, the same layer had to be processed multiple times. That meant a repetition marathon in manufacturing. More steps, more time, more opportunities for error. So the idea whispered in labs for years knocked on the door again. EUV, extreme ultraviolet lithography. In the late 1990s, physicists and engineers said, someday, but no one could make it commercially viable. If Moore's law, roughly doubling the number of transistors on a chip every 2 years, was to hold, this seemed like the only realistic path. On paper, EUV looks simple. Shorter wavelength equals smaller lines. In practice, the devil is in the details. At 13.5 nanometers, this light doesn't pass through air or glass. Classic lens-based methods were off the table. EUV demanded a vacuum inside the machine. The light is so energetic it gets absorbed by everything it meets, including air. Glass lenses absorb it, so you can't use them. Instead, you need multi-layer reflective mirrors. The mirrors used until then absorbed too much of this energy, so atomically smooth mirrors were required, something never produced before. Today, with sources around 250 watts, production tools have reached roughly 160 wafers per hour. Getting here required a source that turns tin droplets into plasma 50,000 times per second, an ecosystem of actinic mask pellicles and resists, and hundreds of improvements across extraordinary mechatronics. This adventure replaced traditional lenses with atomically smooth multi-layer mirrors arranged in vacuum tunnels. Each mirror reflected about 70% of the light. Otherwise, 13.5 nanometer light would simply be swallowed by glass and air. EUV masks needed reflective, phase-shifting designs. Without tools that inspect the mask at its own wavelength, actinic inspection, and pellicles, defect management would be impossible. EUV light is one of the wildest elements in the universe. Hard to create, nearly impossible to control. By nature, it wants to touch everything and be absorbed by everything. ASML's decades-long struggle has been to tame this wild force and turn it into the most delicate artist of the modern world. What they built isn't just a fabrication tool, it's almost science fiction. Each of these gigantic systems, costing more than $200 million, rests on three fundamental miracles. It starts with the light source. Ultra-powerful CO2 laser pulses turn tin droplets, small as a pinhead, into plasma 50,000 times per second. The photons emitted from this plasma sit at 13.5 nanometers. To collect them efficiently, you need long-lived collector mirrors, advanced coatings, and rigorous optical cleaning regimes. Going from roughly 10 watts in early prototypes to hundreds of watts today took years on its own. These photons are reflected to the mask and then to the wafer by Z-made mirrors, brought to atomic smoothness with multi-layer molybdenum silicon coatings. Because losses occur at every reflection, the initial power must be very high. The entire journey takes place in pristine vacuum and a particle-free path. Over the years, actinic mask inspection and EUV pellicle development have been added to this chain. On the stage side, magnetically levitated platforms accelerate with fighter jet-like forces, yet stop with sub-nanometer positioning error. Laser interferometers and image-based measurements perform about 20,000 control updates per second. Wafer handling robots operate at around 2 millikelvin thermal stability. This synthesis of control theory and mechatronics, combined with TWINSCAN's dual-stage choreography, delivers a real solution to the fast and accurate equation. The invisible Orchestra ASML may look like a giant on its own, but in reality it conducts a highly professional orchestra. A single EUV machine contains more than 700,000 parts. About 90% of components come from external suppliers through co-development relationships. Rather than full vertical integration, ASML plays the role of architect orchestrator. It even manages suppliers' financial dependencies to prevent overloading any single vendor. In critical cases, it acquired companies like Cymer and Berliner Glas to keep the ecosystem standing. There are many single-source critical parts in this chain. If the timeline of any one of them slips, production plans around the world roll back. Shipping a machine is an operation in itself, disassembled into special containers. Sometimes through multiple cargo flights and dozens of containers, it reaches the fab floor. The logistics of high NA generations, with 250 shipping crates and double-digit container counts, turns into a kind of flying factory assembly. The rules of the game change. When EUV took the stage, not everything changed overnight, but the direction of the game did. This wasn't just drawing at a smaller scale. It meant achieving higher yield with fewer steps and fewer repetitions. Whereas the same layer once needed to be printed 3 to 5 times, now it could be finished with a single critical exposure. In some layers, one EUV exposure could replace 4 DUV exposures. That reduced process complexity and the probability of defects while shortening cycle time. Still, note that techniques like EUV double patterning didn't vanish at sub-5 nanometer layers, and hybrid EUV plus DUV flows remained present in places. After years of quiet and costly research, ASML's first commercial EUV machine was ready to enter the lines of the world's largest chip foundry, TSMC. It was a multi-billion-dollar vote of confidence. TSMC bet everything on this new, unproven technology to leap ahead of its rivals. The risk turned into one of the most profitable moves in tech history. Thanks to EUV, TSMC could produce nodes like 7 nanometers and then 5 nanometers in a single elegant step that competitors struggled to achieve with complex multi-step processes. Clock speeds, density, and energy efficiency rewrote the rules. Tool throughput approached around 160 WPH in this period, making the economics of EUV finally work. Intel, the undisputed leader for decades, was slow to embrace EUV. That hesitation proved costly. Samsung, determined to stay in the race, had to place EUV orders worth billions. The rule was simple. Either you have an ASML EUV machine, or you drop out of the top technology league. Here the story opens a new act, high NA. Think of it as widening a camera's aperture. By capturing steeper angle light, you can render sharper, smaller details. Standard EUV had a numerical aperture, NA of 0.33. High NA raises it to 0.55. The gain is big, but so is the system. Optics grow massive, and some large chips may need stitching by printing the pattern in two parts. Still, a much cleaner process window opens for critical layers. One of the earliest names to stand out in field trials was Intel. The first XE5000 class machine reached the US in a shipment of hundreds of crates, and installing it became a mega commissioning project in its own right. High NA tools are discussed in the $300 to $350 million range. Earlier EUV generations were $150 to $250 million. These machines travel via dozens of containers, multiple cargo flights, and fleets of trucks. Temperature and vibration conditions of each subsystem are managed separately. And it's not just the machine that's evolving. Resists, mask pellicles, computational lithography, and metrology are advancing in lockstep. It lifts the entire ecosystem together. Technology is power, and power comes with rules. EUV wasn't sold to certain countries from the start. The fuse was lit by US diplomatic pressure on the Netherlands in 2018 to 2019. In 2019, the Netherlands did not approve the first EUV export license to China. In 2020, the US placed foundries like SMIC on the entity list. In October 2022, the US introduced comprehensive controls on advanced semiconductor manufacturing equipment. In March 2023, Netherlands announced that advanced DUV lithography tools would also require licenses, making immersion DUV systems unshippable without them. ASML sees itself as a technology maker, not an arms dealer. But a decision had already been made. The company had become a geopolitical entity that, beyond serving its shareholders, also had to align with the strategic interests of the Western alliance. While the Chinese market still offers strong DUV demand, especially for mature nodes, restrictions on advanced lithography permanently alter the revenue mix. ASML's response has been to lean harder on its most sophisticated EUV platforms and on service upgrade business. At ASML, the story doesn't end when you sell a machine. It begins there. Regular maintenance, optical cleaning, source module replacements, software updates, and field upgrades form a major share of the company's revenue. Elevating an existing tool with new parts and software is cheaper for the customer than buying a new machine, and faster for the line to benefit. This is the company's more resilient revenue stream. Even when the market slows, production doesn't stop. As long as machines run, demand for service and upgrades continues. And these lines of business are often more profitable than hardware sales. As of 2024, roughly 25 to 30% of total revenue comes from service and field options. In Q2 2025, installed base management sales were 2.1 billion euros, within 7.7 billion euros of revenue. Consumable optics like collector mirrors, CO2 laser modules, immersion fluids, and calibration metrology software form the backbone of this cycle. ASML has a large engineering workforce operating 24/7 in the field, planned maintenance windows that minimize downtime, tool-to-tool productivity packages, and software licenses. The installed base functions like a revenue annuity for years. The company still delivers performance improvements even 10 to 20 years after first install. Even systems like the older PAS 5500 remain in production in some cases. We can imagine three simple pictures for 2030. Scenario 1, an accelerating world AI hunger persists. Data centers, HBM, and advanced nodes open the door to high NA more quickly. In this scenario, 0.55 NA reduces repeats in certain critical metal/contact layers and broadens the process window. Shared gains in throughput and yield determine the speed of HVM adoption. This transition also depends on compressing high NA logistics and installation times. Scenario 2, balanced world AI growth settles into a normal rhythm. Standard EUV and advanced DUV remain very strong. High NA is used selectively in critical layers. EUV's role in reducing multi-patterning is preserved. Even below 5 nanometers, EUV double patterning and hybrid EUV plus DUV flows are still seen in places. Scenario 3, constrained world. Macro shocks and restrictions weigh on investments, yet the installed base's service and upgrades cushion the company. Here the razor and blade analogy of ASML's business model, tool plus service, kicks in. Years of field know-how and upgrade packages soften the way. Across all three scenarios, packaging grows but doesn't eliminate lithography. It redistributes the need. Chiplets and 2.5D/3D packaging are powerful levers to boost performance without shrinking the node. Critical dies are still printed at advanced nodes. Interposers and redistribution layers require their own lithography. In short, packaging complements. It may ease pressure on leading-edge nodes in places, but it doesn't erase lithography demand. At such tight tolerances, the supply chain becomes fragile. Zeiss optical capacity, collector mirror lifetimes, source stability, stochastic effects and resists, metrology, and inline inspection. Maintenance, such as cleaning or replacing collector mirrors after certain shot counts, or periodically swapping source modules, affects planning by itself. Add geopolitical uncertainties and licensing processes, and timelines can slip with tiny adjustments. That's why ASML's real skill is not just the machines, it's marching hundreds of niche suppliers in the same rhythm. Step back and consider this simple sentence. ASML's Moat isn't just patents, it's the learning curve, a shared engineering culture, the orchestration of single-source critical parts, and a tradition of co-development with customers. These are capabilities money can't copy quickly. That's why the competition isn't a sprint, it's a long, patient ultramarathon. Today, ASML is the sole supplier supplier in EUV. In total lithography, people speak of market shares approaching roughly 90%. That scale, more than 42,000 specialists and machines with over 700,000 parts, supports the claim of being the most complex product in the world. Two lines appear on the horizon. First, the maturation of high NA. Sharper edges, fewer repeats, a safer process window. Second, beyond EUV ideas, far more exotic sources, entirely different writing techniques, or redefining the whole architecture through packaging. Whichever comes first, one thing is certain in the near term. The light guiding our path will still be EUV and its magnified version, high NA. And let's end where we began. The tiny tap you make when you silence your alarm rests on the synchronization of hundreds of thousands of parts, some working in a hall in Veldhoven, some in an optics center in Germany, some in a laser lab on another continent. You can't see them. The modern world's skeleton is built from them. So the answer to our question is now clearer. Yes, sometimes a single company really can change the world's rhythm. ASML's story shows this. Technological leadership isn't won overnight. Rising from a leaky shack in Veldhoven to today's global hegemony took over 40 years of patience, resolve, and engineering excellence. Along the way, the company repeatedly faced bankruptcy threats, was underestimated by rivals, and invested billions in impossible projects. Today, ASML occupies one of the most interesting paradoxes of the modern world. A Dutch company most people have never heard of actually controls the most critical bottleneck of the digital age. From your smartphone to your electric car, from AI servers to medical equipment, everything depends on chips that pass through ASML's machines. That dependence is so deep that the company's production plans directly influence national tech policies, geopolitical balances, and global power structure. The development of EUV is a success story that stretches the limits of human endeavor. Controlling 13.5 nanometer light, turning tin droplets into plasma 50,000 times per second, producing atomically flat mirrors, and coordinating all this with sub-nanometer precision was unimaginable in the late 20th century. ASML and its partners turned that dream into reality. The core philosophy behind the company's success is also striking. Instead of full vertical integration, ASML embraced an open innovation model. By working with the best suppliers around the world and allowing each to reach excellence in its domain, the company created a synergy that rivals cannot copy alone. Zeiss's optics, Cymer's light sources, and the precise mechanical parts of hundreds of small suppliers combined to form an ecosystem beyond imitation. With high NA coming online, the story enters a new chapter. A 0.55 numerical aperture pushes closer to the limits of physics. But ASML's engineers are already thinking beyond EUV. Perhaps the future will bring even shorter wavelengths or entirely different writing techniques. Or maybe chiplet and 3D packaging will take the place of Moore's law. Whatever happens, one thing is certain. Technological progress won't stop. Humanity's hunger for faster, stronger, more efficient computation will continue. And at the center of the solutions that meet that hunger will likely be invisible, yet indispensable companies like ASML. ASML's story is also an example of globalization and technological interdependence. A Dutch company keeps the world turning by working with German optics, American laser technology, Japanese chemicals, and Asian customers. This complex web shows the power of international cooperation while reminding us how dangerous geopolitical tensions can be. Export restrictions to China show that technology is no longer merely a commercial commodity. It is seen as a strategic weapon. Access to semiconductor technology, like oil in the 21st century, sits at the heart of power and sovereignty struggles. Whether it wants to or not, ASML has found itself in the middle of this game. The company's service and upgrade business model also reflects the character of the modern tech economy. Selling the machine is only the start. The real value lies in a relationship that lasts years. Continuous improvement and know-how transfer. This model shields the company against economic cycles while enabling deep, lasting bonds with customers. ASML's future is intertwined with that of the tech industry. If the AI revolution continues, demand for more powerful chips will speed high NA adoption. If there's an economic slowdown, managing the installed base will matter even more. If geopolitical tensions rise, supply chain diversity and geographic balancing strategies will become critical. Ultimately, ASML's story teaches us this. Innovation isn't linear. Success requires not only technical excellence, but also strategic vision, the courage to take risks, long-term thinking, and ecosystem management. The journey from a leaky shack to a global giant shows the reward of patience, persistence, and belief. And perhaps most importantly, ASML's story reminds us how fragile and complex the system beneath the modern world really is. Every time you pick up your phone, sit in a car seat, or browse the internet, you're standing on this invisible skeleton. Companies like ASML form the foundation of our digital civilization. If you enjoyed this journey, don't forget to like and subscribe. Which topic should we dive into next? The first production results of high NA, the behind-the-scenes world of masks and resists, or the packaging revolution? Your comments and guidance are very important to me. I'm Halil Ibrahim. Thank you for your time. We'll continue exploring the hidden face of our lives in the next video. Until then, take good care of yourselves.